Welcome to another fascinating aspect of physics, system of particles, and center of mass. Now, system of particles is a collection of objects, while center of mass is a key concept used in calculating the motion of system as a whole. These two concepts are essential in understanding the behavior of matter and energy in our universe. They have numerous applications in fields like astronomy, engineering, and even in our everyday life. Therefore, let's go together on this very interesting adventure. First, we look at the definition of these terms. System of particles refers to a well-defined collection of many particles. Also, it is a collection of objects that may or may not interact with each other. As I said earlier, it is a fundamental concept in physics, and the understanding of this concept is crucial in studying the behavior of matter and energy. An example of system of particle is a rigid body. It's made of particles at fixed positions in the system. Rigid body is made of several particles at fixed position in the system. Center of mass is a point in a system of particles where the total mass of the system is evenly distributed. The center of mass is a key concept in physics, and it is used to calculate the motion of the system as a whole. Also, center of mass of a system of particles is the unique point at the center of a distribution of mass in space that has the property that the weighted position vector relative to this point sum to zero. So the point in a system of particles where several other the masses of the particles that make that other system, where they tend to act at, the resultant action of the individual masses tend to act at that point that is called the center of mass. And lastly, center of mass of the system is the point that moves as though all of the system mass were concentrated there and all external forces are applied there. It is that point in the system of particle where it appears as if that's where all of the body mass is concentrated. So that's just a very short illustration definition of center of mass. And it can be computed. You can determine the center of mass for any object. In this case, you are looking at rigid bodies. And the center of mass can be estimated from the expression x subscript cm. That cm means center of mass. So x is the position of the center of mass. Position of the center of mass. The x is the position of the center of mass. Cm subscript is center of mass. And to obtain it, it's summing up the product of each of the masses of the particles, the mass of each particle in that system, and the position of such particle. Sum the product of this, then divide by the total mass in that system. Again, to obtain the center of mass of a system of particles, you sum the product of the individual masses and their respective position, and you divide by the total the summation of each of the masses in that system. And that's what you see in the first expression there, which can be represented as that sign, summation from I equals to 1 to m subscript I, s subscript I, divided by summation I is equals to 1 to m subscript I is the position of each, or let me say, sorry, the identification of each of the masses. So the first of the particles, the first particle can be tagged as 1, the second particle 2, third particle 3, fourth particle 4, n number of particles. So if you have 5 particles, n will be 5. If you have 10 particles that make up that system, then n will be 10. I believe you understand. So that's how you tackle that. And the summation of the individual masses, what you have at the denominator, can be represented further by capital M. By capital M. That's why you now have the expression 1 over capital M summation of M, product of M subscript I, S subscript I. In 3 dimensions now, instead of using X, we use R. In 1 dimension, in the X-axis, you use X. In Y-axis, you use Y. You see what let me use the pen. X-axis, you use X. In Y-axis, you use Y. In the Z-axis, you use this. But in 3 dimensions, you use R. Because R is a function of X, Y, and Z. 3 dimensions. So R is X, center of mass of the x-axis, center of mass of the y-axis, and center of mass of the z-axis. And IJK just telling us that those are different direction, perpendicular to one another. We can see examples, very easy examples of how to apply those expressions. For example, we have 2 point masses, 3 kg and 5 kg. In this case, the system of particles is just made up of 2 bodies, 2 particles. And the first particle has a mass of 3 kg, while the second has a mass of 5 kg. And the position of the first particle from a predetermined point, the origin, next axis, is 4 meters, while the position of the 5 kg particle is 8 meters. The question is, we should determine the center of mass from the origin and also from the 3 kg mass. It's very straightforward. So in this case now, we can call this your M1, and you have M2. And this will be what? On x-axis, so we have x1 and 8 x2. And from there, you solve. So let's go to the next slide. You see the solution. You see this? This is the origin. The origin is here at 0. So M1 is placed 4 meters from the origin, and M2 is placed 8 meters from the origin. So the center of mass from the origin, that's the first part. Using our formula, M1x1 plus M2x2, recall that we have just 2 masses, so it's terminated after 2. M1x1 plus M2x2 divided by the sum of M1 and M2. So we have 3 kg You have 3 kg, that's M1, times 4 meters, X1, 5 kg, M2, times 8 meters, X2, then 3 kg, M1, 5 kg, M2. So we have 12, you have 12 kilogram meter plus 5 times 8 is 40 kilogram meter, then over 3 plus 5 is 8 kilogram. No, this one has no meter. There's no meter there. Okay? There's no meter. It's this 8 kg. So that means we have 52 kg kilogram meter over 8 kilogram. If you do that, then you will have 6.5 meters from the origin. But the second case, if the center of mass is now at where the position where we have the 3 kg mass. So with reference to the position of the 3 kg mass, M1 will be 3 kg. But the 3 kg mass from that position is 0. The distance between the 3 kg mass and that reference position is 0. You get it? If you bring the position for center of mass, the assumed position, where you have the 3 kg, then the distance x1 will be 0. Because 3 kg is lying on that same position of interest. So this term is 0 then. And the M2 from that 3 kg will be 4 meters. 4 meters. Recall that from the origin, M2 is 8 meters. And from the origin, M1 is 4 meters. Therefore, the distance between M1 and M2 will be 4 meters. So that's why we have 4 meters. So 5 times 4, you have 20 kilogram meters over 8 kilogram. And when you solve that, you have 2.5 meters. Another example. In this case, we have 3 particles making up a system, or 3 masses making up a system of particles. 3 masses making up a system of particles. And however, that system of particles is not a linear, or it's not on the straight analysis. It's on a 2-dimensional plane. That system of particle is not on a 1-dimensional plane, rather it's on a 2-dimensional plane. So you have three kg as M1, 5 kg as M2, and 9 kg as M3. And these 3 masses are located on a meter plane with respective coordinates. The respective coordinates shows that this coordinate belongs to the first mass, then the next one to the second mass, and the last coordinate to the third mass. Likewise, for each of the coordinates, when you have 2 values like this coordinate, then the first is x and the second is y. Therefore, here this one will be s1, y1. Likewise, the second one coordinate 20, x2 will be 20, and y2 will be 5. And the third coordinate, x3 will be 5, and y3 will also be 5. So we now see how we apply that. We call our formula again. To get center of mass, we solve the center of mass for the x-axis and also for y-axis. To do that, we find the summation of m I f I from I equals to 1 to n, and in this case our n is 3, and summation m I from I equals to 3. And likewise for y, same thing. We have that, although it will now be m I y I, the summation m I. Likewise, I equals to 1 to 3, I equals to 1 to 3. So let's see the full solution in the next slide. So remember we said our m1 is 3 kg. So you have m1 3 kg, x1 0, that's 0 meters. Then m2 5 kg, x2 20, m3 9 kg, and x3 5. So you, for x, you have center of mass on the x-axis, you have 8.53 meters. Then you repeat the same for y, picking the y value, 15 for m1, 5 for m2, and 5 for m3. And you also substitute, and you also obtain 6.76 meters. So center of mass will be the value there, 8.53, 6.76. Another example, you have 3 masses, m1, m2, m3, and these 3 masses form an equilateral triangle. Equilateral triangles is a triangle which have equal sides, the length of the sides are equal. So the point here, point here, point here. Equilateral triangle means these sides are equal. So you have a m1, m2, m3, mass 3. Okay? So this is the coordinate. So 0, and the edge length is 140 meters. I mean each of the length. This side is 140 centimeters. This side is 140 centimeters. Likewise, this side 1 centimeter. That's what they mean by that. So you have to obtain. You can see that with this now, that means we are dealing with 2 planes too. The x plane and the y plane. So let's go to the solution and let's see how we do it. You see it? This again is m1, the 1.2 kg is m1. 2.5 is M2, and 3.4 is M3. No specific position is provided, so no matter the position you place them, please, they are equilateral triangle, then you obtain the same final answer. Okay? So to obtain for x1, we know M1, we know M2, we know M2. But to get our x1, the position of M1 is at this point, the 0, 0 position. Okay? The origin. So x for M1, S1 will be 0, Y1 will be 0. Straightforward. For M2, because the edge length is 140 centimeter, so for M2, our x will be 140, but because it's on this edge, y is 0, so y2 is 0. Then M3, for M3, we obtain x3. How do we obtain x3? What is it? We trace down the position to the x-axis. You see that black broken line traced down to the horizontal axis, x-axis. So the distance of this point, that's black ink here I'm shading, to the origin, that's x3 for M3. Likewise, trace this line, the position of M3 to the y-axis, vertical axis. That position gives you y3. And how do you obtain that? To obtain S3, since the triangle is equilateral, midpoint, that means the point, vertical point from the mass M3 to the horizontal axis will cut that line midway. So that means it will be from that center to the origin will be 70 meters or 70 centimeters. That's why our x is 70. And for our y, to obtain our y, where I marked to obtain our y3, this, to obtain our y3, what do we do? Sorry, to obtain our y3, we know our x already, and we know this slanting side of the equilateral triangle, which is 140 centimeters. So use Pythagoras theorem. Call that slanting side the hypotenuse C. Call the x side, call it A. Then the unknown side y3, call it B. And call about that Pythagoras theorem says C squared is equal to B squared plus A squared, C squared. So B is the unknown. So B squared is equal to C squared minus A squared. So if you substitute 140 squared minus 70 squared, we obtain the value 121.24. That's what I'm writing. So now that x1, y1, x2, y2, x3, y3 are known, then you substitute the formula and you obtain the center of mass, which will be xcm, center of mass on the x-axis will be 82.3, and y substitute cm, center of mass on the y-axis will be 58.1 centimeters. Now this is a little bit different, but it's also the same approach. In this case now we use the direct formula. We call that the position vector r is xi plus yj plus zj Okay, so we are given the position to R1, R2, R1, R2 for mass M1 5 kg and mass M2 3 kg. So straightforward. Let's see the solution. So instead of now using x1, xy, because it's given as a vector quantity, straight, use a vector notation R. So you have the center of mass will be the formula 1 over capital M. That capital M again is the total mass, sum of the total mass, sum of the masses, total mass. Then multiply by the product of the summation of the product of the individual masses and their respective positions. So to do that, M1 R1 plus M2 R2. Remember, we have two masses over M1 plus M2. So M1 is 5 kg and R1 is that expression. Then M2 is 3 kg and R2 is this expression. So open the bracket. 5 times minus 2 minus 10i, 5 times j, 5 times 1 j, but j means 1j, that's 5. 5 times 5 a, 25. Likewise 3 times 1 3, 3 times 3 9, 3 times 4 12. So sort the like times, get the like times, and we solve. So you have this expression. Here, 7 by 8 is the x, 14 by 8 is the y, 7 by 8 is the z. So you can represent the position of the mass on the coordinates. Here you have z, you have y, you have z. You can represent it and determine where the position of the center of mass of the system will be. There are several other ways of obtaining center of mass of rigid body. For example, we have solid bodies. Maybe like a rod, like a disc, like a sphere, then you can also use this expression, the integral notation to any center of mass. Here you have 1 over capital M. Remember, capital M is the total mass, the sum of the individual masses that makes up that system. The integral of x dm. Dm is the elemental mass. These particular expressions are much beneficial when such solid bodies are assumed to be uniform. So you just take an elemental mass, dm, and integrate over the entire body to take the final expression. We'll see examples. So we can solve for the volume 2. Do that. Let's see the example that we have. Look at this rod. The rod is L long. The length of the rod is marked as L. And since it's just a one-dimensional object, rod, the breadth is far lower than the length. So it's assumed to be a one-dimensional object. The breadth is very small compared to the length. So in that case, you tag the mass in terms of the unit length. So you work with the linear mass density. which is represented as lambda. Linear mass density is measured in kilogram per meter. Kilogram per meter, linear mass density. That's how you work with it. And that means a small elemental, for a small element, a small part of the rod, small part of the rod, the mass of that small part can be obtained. For a small part called as ds, if you check the diagram, this small part falls at ds, a small part. Remember the rod was uniform. That the question says a uniform rod. So the mass of that rod will now be the product of the linear mass density and the length of the little portion cut off. That is, if I take any of the same length, yes, if this, for example, is 5 centimeters, and I come here and take another 5 centimeters, this area, 5 centimeters, I get it. Look at the area I'm shading on the diagram, 5 centimeters. Or I come here, I pick another, I put another area, 5 centimeters, and I measure. There we have the same mass. That witness, the same mass. So I will recall that lambda is m over n. So the m is of the m, the elemental mass, which is lambda ds, is capital M over n ds. So using the integral form again, where you have the m, go to your capital M over n ds, and so you integrate. M cancel. And because we are dealing with a rod, so the limit of our integral will be from 0, the beginning of the rod, to L, the end of the rod. So M will cancel M. So you have 1 over L. Remember, the rod is a constant. 1 over L, bring it out. So the length of the rod is a constant. And you have x ds. So integrate. X ds is s squared over 2. Now you put the limit there, and your x, the center of mass of the rod, will be L over 2, that is the midpoint of the rod. So what does that mean? That means if you have a 100 meter long rod, that means if the rod is a uniform rod, that is, the weights, the masses are evenly distributed across the length of the rod. If it's a uniform rod, then the center of mass, the total mass of that body will tend to act at the midpoint of the rod. So the center of mass will be at the midpoint. That's what it means. So if the rod were to be 100 meters long, then the center of mass will be at 50 meters. That's 100 meters over 2, 50 meters. But if it's not a uniform rod, then you don't expect it to be at the center. If the distribution of masses is not even in the rod, then you cannot obtain it. As I said, this formula is particularly for objects that have uniform distribution of masses. Likewise, for circular disk of mass m and little, you can determine the center of mass. Now, this is a disk. What is a disk? This is 2 dimension. So in this case now, we are not dealing with linear mass density, we are dealing with area mass density, represented as sigma. Remember linear mass density is m over l, or dm over ds, a length. But in this case, it is dm over da, area, not length. And for a disk now, the area of a disk is pi r squared. So depending on the object, if it will be a rectangle, if they use a rectangle, you know that it cannot be pi r squared. Okay, it won't be pi r squared. So if you have that, then your expression x, our point of reference, is at the origin. X. Because remember our formula is 1 over m s tm. But we want to say center of mass will be what? We are taking it as SM as two plane xy, because we're talking about area mass density. We have 1 over capital M integral of r dm. Okay, so r dm. That means at the center r 0, and the limit is from 0 to r. So if you solve, you're going to be at 0. Be at 0. If you want to determine the center of mass, midpoint between away from the center of the disk. At that point, I will have it to be r over 2. My small r will be r over 2. You get it now? R over 2. So work with that. But in this case, from the center. So that you have the center, you have center of mass will be 0, x, 0. That is at this point, this center, this x, this y, in line with coordinates 0, 0. And it's true for a uniform circular disk. If this disk is uniform, if the masses of the particles that make up that disk are evenly distributed, then the center of mass will be at the center of that disk. That works. Thank you. So just study. If you have further questions, you can put in the comment section. I will respond to it. God bless you.